Good afternoon, ladies and gentlemen. When I initially got this time slot, I thought, oh no, after this day of people talking about stuff, there will be very few of you left. I'm really happy to see a fully packed audience. Great, thank you very much. We're going to speed up a little bit. I'm a racer at heart. I'm a design engineer. I spent my whole career designing more or less armored vehicles. I started off as a rocket scientist. Yes, I worked at Kentron and I was responsible for the flight control mechanics of the ZT-3 anti-armor missile. So it's flying very close to the wind to say that I'm a rocket scientist, but it makes for a good story. I'm going to have some good stories for you. So we started developing two brand new 500cc single-cylinder two-stroke motorcycles on the 25th of February this year. With nothing. Honestly, nothing. A clean sheet of paper. And our plan was to participate in the Roof of Africa Extreme Enduro in Lesotho in 2 weeks at the end of November. Do the math. That's not a lot of time. So when I was asked by I can't remember if it was Elton or Joshua that asked me to do a talk today, I thought, damn, we haven't anything to measure. So what am I going to talk about? Measurement, and that's their forte. So I thought, well, they do a lot of technology stuff, all the instruments and the software and the stuff, and it's great. I mean, we've just listened to, my mind went like, well, pixels by pixels by pixels. I'm trying to calculate because I'm a photographer as well. How many bloody megapixels is that? And I just, awesome. Any case, and then I came upon a great idea. I thought, why not tell you what we did and how we did it, how we selected relevant technologies to get us to where we are today. The bike's running, it's ready for the roof. We designed, manufactured and built a complete new engine in 7 months and 20 days till we started it the first time. That's just crazy. You've got to do a couple of things right. And one of the things that we did right is myself and my partner, Rempies, we have a lot of experience in development and design, and we chose relevant technologies. This means that sometimes we used Excel spreadsheets and made a calculator out of that and did analysis and simulation with that. Sometimes we used our gear expert in the UK, Piet van Zyl, who's an ex-South African. He uses very sophisticated gear calculation software to develop some specialized gears for us for the bike that's going to participate in the roof. Sometimes we just use our heads. Sometimes we use artisans to do work that would otherwise be done by complex machines. We use modern technology, and I'm going to, before I go into that, how we chose the technologies, let me just put into perspective for you the age that I am. I'm 67, and what happened with technology in my time. Back in 1969, Apollo 11 landed on the moon. The computer that did the navigation weighed 32 kilograms. This is a NASA computer. This is something that goes into space. It weighed 32 kilograms. So it's like 2 bags of cement. Just imagine that. It had less computing power than, and this is not a fancy phone, but I guess any one of your phones will have more computing power than that. 1969, I was 14 years old. In 1975, we got TV. If any of you remember that test pattern, it dates you. 1975, I was post-matric. I was in the military academy, getting ready for my engineering studies. In 1976, I joined the University of Pretoria to study mechanical engineering. We were the first year group that were allowed to use electronic calculators. Up to that stage, the guys used slide rules. Anybody remember a slide rule? And logarithmic tables to do complex calculations. 76, sorry. In 1988, I worked at Ermitech, which later became BAE Systems OMC. That was the design and development facility for them. In 1988, we got our first fax machine at the factory. Before that, we used a telex machine. Do you know what a telex machine is? That bad baby up there, that's a telex machine. That thing will spew out the words like that. It's like a old type telegram. It's just a little bit faster. You can put more data in it. And in that time, our company developed the Roycat 8x8 infantry. What is it? It's an infantry. It's not a combat vehicle. It's a tank killer. It's supposed to be a tank killer. It's got a 76mm gun on it, and it's supposed to take out tanks. And the reason why it's got wheels as opposed to the European vehicles of this type that all have tracks is because we were fighting the Bush War in Namibia. Long distances to travel, and this is not where you want to use a tracked vehicle. Right, and then in 1994, we got the wonderful cell phone. By the way, interesting, I read that a cell phone is the second jump technology in the last, I reckon, must be 300 years or something, which means that jump technology means that people that previously did not have access to a specific thing, suddenly, because of what was in place at the time, suddenly they have a new means of doing that. So the first one was the train. Yep, believe it or not, the train. The train opened up America, the train opened up Europe. It made long distance travel possible. They built a railroad from the east coast to the west coast to get stuff to the west. Go west, young man, go west. That was the first jump technology. The second jump technology was cell phones. People who were previously disadvantaged in not having money to have a landline installed in their home, they suddenly have a cell phone. You stop at any bus stop, any taxi rank in South Africa today. You'll see them. They've got their cell phones in front of them, they're logged into Tshwane's Wi-Fi, and they're good to go. That's a jump technology. And that only came to South Africa in 1994. The first cell phone, the thing to have, was the so-called Nokia brick. It was, I think it was what, 1011 or something like that, a little fold-out antenna. Man, and that thing would break. That was really not lacquer, but the battery lasted more than a day, and you could type, A is number 1, C is you press 1 3 times. Can any of you remember that? Yes, I can. Okay, so these are technologies that happened in my lifetime. So sometimes I get confronted by these young kids, fresh out of varsity or before varsity. Actually, varsity takes a little bit of that windgatheid out of them because they realize they're not as cute as they think they are. But high school kids, they think they are the happening generation. Well, I've got news for you, sonny boy. It's my generation that made all that stuff that you're so bragging about. So think about that. Okay, enough of the lecture. So how we selected and used relevant technologies. And by relevant, I mean, yes, you can get really fancy. For instance, we use an Excel spreadsheet that was generated by a friend of mine at Ermitech way back in 1988. I still use it to do tractive effort simulation. There are software packages available. Our OnScore friends will know about VB Drive. But the problem with VB Drive and a lot of those things, if you're thinking about vehicle dynamics, there's atoms. There is so much stuff that you must have and gather and get together and input into this thing before you can get some kind of an answer. I work on the 80-20 principle, the Pareto principle. So you focus on the 20% that makes 80% of the difference. And to do that, I need quick turnaround. I don't want to sit for weeks waiting for ZF or somebody to give me a matching curve of the torque converter with the engine curve. By that time, I've already used 3 different engines and 2 different gearboxes. Time is money. We've got to move on. So in that particular model, I just input the torque multiplication factor, and I do a simple straight line from 0 speed to maximum torque band. It's a dashed line, and with that, I've got excellent results, I know exactly what I want, I can have it like that. That's relevant technology. That's not spending days and weeks inputting data into a stupid simulation package that gives you answers that are better than mine. But guess what? That VB Drive and other simulation packages for driveline simulation that I've used in the past will give you the acceleration 0 to 60 kilometers an hour of an armored vehicle. That's generally in the region of 16 to 18 seconds. It'll be out by at least 2.5 to 3 seconds. What the hell is the use of that? Okay? You spent these weeks and it's out by, I mean, what's that? It's more than 10%. And it makes a killer difference if the customer is hell set and hell bent on achieving a specific number. Okay, so let's hoy. How we selected relevant technologies. One of the team members, Niels van Niekerk, did his honors degree in developing a engine combustion cycle simulation package called Vanik. His trade name is Vanik. He's on the internet, vanik.co.za, and you can buy the software and it does. So what we've got here is on the left-hand side is the input panel. On the right-hand side is 2 predicted power curves for our motorcycle, the one that's going to be competing in the roof of Africa. And the one is with the power valve open, the other one is with the power valve closed. I'm not going to bore you with the details, but a power valve is like VVTi. It's only happens in a 2-stroke. You're lowering the exhaust port, so you're getting less radical exhaust gas escaping at low RPM, gives you more torque at low RPM, smooths out the power band. So that's good technology. It's used by a lot of international companies. We bought, we had the clean sheet was somebody's old gearbox that we used. By the way, we didn't develop the gearbox itself. We used the gearbox and the clutch out of an existing KTM 300 for the roof engine, and for the Bonneville engine we had to up the ante, and we're using a KTM 690 gearbox for that. But the rest is all our design: the crank, the barrel, the head, the casings, the katoot. The whole thing is ours. So instead of using a very fancy and expensive 3D measuring equipment, we clamped the casing upside down on a CNC milling machine. And these days, just about every CNC milling machine has an XYZ readout, and like that. That's because what's critical is you've got to get the center distance between the shafts, and you've got to get the depth from the mounting face to where the bearings sit. We did that on a milling machine, not on a fancy 3D scanner, so or 3D measuring equipment. Relevant technology, and just about every machine shop in South Africa has this capability. Very few of them have 3D measuring equipment. Piet van Zyl, who is a world-renowned specialist gear designer, he worked for McLaren for, I believe, he left from South Africa. He was my friend here. He left for, and worked for McLaren Formula One and designed the gears in their gearbox for 14 years. He was, his gears was part of the car that won, I think, 2 or 3 world championships. So this guy knows gears, believe me. He knows gears. And during the process of, he had to design the primary drive gear that sits on the crank and that drives the clutch. And then through his connection with Niels van Niekerk, we also know, so by the way, we all studied at Tux, you know, Tux of ducks, one of those things. So, and we're all old toppies. And he talked to Niels, and Niels said, but they discovered recently that there's a huge fluctuation in crankshaft speed as it rotates. You've got the induction cycle, then you've got the compression cycle, where the thing is slowed down because it's doing work, it's pushing the air, it's compressing the air. Then it gets to the top, and then all hell breaks loose. And that's where the fire starts, and this thing accelerates to the bottom. And it was said that this slow down and speed up of the crank induces incredibly high instantaneous loads on the gears. Remember, these gears are seeing this every cycle. And he was very worried about this, and eventually it's just as well that he was very worried about this, because it turns out that the forces on the gear teeth, I can't remember the exact number, that's Piet's domain, but it was something like 2.5 times if you just take the mean. So it's just as well he did this, and what he did was, and I'm just going to play you one or two short, not that, this is not my laptop. Whoa, I can get this. You know, I was born in 56 and that bred on tough and ingenious.
Initially we speed up the crank like a starter would to about 1500 RPM. After about 0.25 seconds we turn off that motor, which means from that point the crank will be running based on its own inertia. And then we start applying the torque coming from the piston onto the conrod, and we carry on running that simulation. Motor turned off, it's only the inertia that is now the resistance, and what we get from that is a graph where we can see the blue here represents the torque going onto the crank, which is 0. Turn that on at 0.25 seconds. The orange line is the balancer torque. As it speeds up, that torque increases, and the moment we turn on the crank torque, which gives us some oscillation, we can now see the balancer torque increasing. We can also see that the balancer is out of phase with the crank, showing that it's doing some work to reduce.
In any case, what he then does is, and this is done on SolidWorks, this is not some simulation package, this is once again relevant technology. He sat down, he saw that SolidWorks had this capability to do dynamics, took him a couple of days, figured it out, did it himself, got a graph out of that which gives you the fluctuations of the crank speed, and I must, okay, I'm going to, can I help? Wait. You know Michael Jackson with his white gloves? Okay, so that's the output of it. That's the speed up, speed down. And there are two gears there. The one gear drives the balancer shaft system. And I thought, you know, really, it's just a balancer shaft that goes round and round, twirly. There's no force on it. But because of the speed up, speed down, and the fact that it's a balancer shaft with two counterweights on each side, one on each side, this thing sees a lot of torque, sees force on the gears. So what's interesting about this, and he talks about it, but I'm going to just skip over it, is that if you look closely, the two peaks are contra-rotating. No, contra-rotating is the wrong word. They're out of phase, because the balancer must be out of phase with the crank. And it comes out of his simulation, and that's how he did it, and he calculated the gear life. And in the end, what saved our bacon is wheel slip torque. The experienced design engineers, vehicle design engineers here will know that sometimes that's what saves your ass, is wheel slip torque. When the wheels are spinning, that's the maximum amount of torque that you can get through the driveline. And in this case, because it's a dirt bike, the traction coefficient is relatively low, and that saves his bacon. The second thing that saves our bacon is the fact that we're going to do the roof of Africa, and after that, I believe we're just going to park it in the garage and look at it. Okay? So those two factors made that we have a safety factor of less than 1.2 on these gears. We're just hoping and praying. Gear life calculations, the same thing. Piet did the calculations and then he shared it with me, and we had a safety factor of 0.7. And I said, wow, that's not going to last a long time. And he said, yeah, and so we went through the scenarios, and with the experience that I've got as a vehicle design engineer, we put in these other things, and I think our service life for this gearbox is less than 150 hours. Now for a racing motorcycle, that's actually a long time. The Formula 1 gears that Piet made for McLaren way back when, one race, and take all the gears out, dump them, new gears for the next race. Man, just to give you why I'm saying man. The primary drive gear and the gear that drives the balancer shaft on this was manufactured through Piet in the UK. I'm not going to allow you to guess how much it cost. I'm going to tell you. 100,000 rand for 2 gears. Using streamlined technology. All right, so can you imagine what that Formula 1 gearbox costs each time? It's just skrikwekkend. All right, and then what we did was, when we started off the process, we had this KTM 300 engine casings, whatever, and we 3D scanned all the components. Then we banged them together in one model, and then Rimpy started with that. So our young engineer, Jock, who is responsible for all our video stuff, put this video together for me. So it starts off with a 3D scanned engine, then Rimpy started designing the casings, and bang! There you've got PZ490. Lekker, just like that. Isn't it wonderful? We live in this age where everything happens instantly. Look at how quickly we design. So we used 3D scanning, but 3D scanning, my friends, is not very usable. Not yet. Because that freaking engine is about 500 megabytes. It's unusable. Eventually we resorted to measuring the casings on the CNC milling machine and just using those measurements, and you have the thing next to you and you look at it. We did the same with the PZ500 gearbox, the KTM 690. At that stage of events, we still didn't know how useless this technology is actually for this kind of thing. There's other stuff where it's useful, and I'll show you just now. You know, don't dump we need baba met die badwater ingooi. Be careful. So the next thing that we used extensively is 3D printing. Man, that works. That is helpful. This is really amazing. So what you can see here, the left-hand picture, it's really critical. There's a little part in the gearbox, and you can see it on the right-hand picture. Okay, so I've got a pointer. On the left-hand picture, you can see there, this is a template that Piet made. So this is the center of the gear shift drum in the bearing. There's a little island that stands out around which the return spring must index. So when it goes to the one side, the return spring will pull it back to that, and it's 0 there, and then when it goes to the other side, it will also stop. And there is your gear shift shaft position. And remember, we had this thing 3D scanned, and we also had it measured on a measuring table, but still Piet was in trouble. This was his 3rd attempt to get the dimensions of those things net to a lekker. And you can see how simple this thing is, and it's incredibly effective. All right, and there what he did was, from that, he then printed a part of the gearbox and inserted all the relevant components. There's your shift drum, the indexing piece that's got the 6 speeds, each one of it's got a little pin. There's your gear shift shaft with the fingers that index on those pins that will shift up or shift down. On this side, you just can't see it, is the spring that indexes on that point there. And this is your detent that makes it click into gear and stay into gear. All of these things, the dimensions are critical. We use 3D printing for it, reverse engineering. We had the casing, the original KTM casing, so we reverse engineered it. By the way, I bought a 3D printer for Rimpy's here in South Africa, and when Piet started battling in UK, I bought him a 3D printer as well, because our casings are so big Both of them had 3D printers, but too small. So I bought, and it's not, we're not talking a lot of money. It's amazing. 400 by 400 millimeter bed, 15,000 rand. If it wasn't for that, we would be up the creek with no paddle. I wanted to use another sentence, but okay. So there's another place where we use 3D printing, and this you'll see a couple of times. We 3D printed the engine casings. Now it works. So we 3D printed the engine casings. There you can see one of the engine casings of PZ500, the bottom of the bike. There you can see the CAD design of the frame. And what we then did was, I jigged all of this up, the rear swing arm, the front forks, and the engine all in their relative position on the table. And then I had to use my brain and my experience. No technology. I lied. The technology that I used was cordless tools, cordless power tools. The freedom that a cordless angle grinder gives you is incredible. Okay, the speed and the safety of it, because you're not tripping over the wire. Okay, so another place where we use 3D printing, and it's because of the size of these casings that we had to buy new 3D printers that are of a proper size. It takes 5 days to print that casing, but it took 2 months to billet machine the casing, so this is faster, much faster. And it gets the job done here, because what was interesting is we're not designing the frame on CAD, because we haven't got the resources. And I've built frames for my road racing motorbikes in the 80s. I drew it out 10 scale on a piece of paper, put it on a jig like this, and started building the thing. So that's what I'm doing at the moment. I'm building it physically. I'm sitting there next to it half the time, I'm just sitting there. You know that gorilla, no, it's an orangutan. There's this picture of this orangutan, and below it's got this subscript. It said, sometimes I sits and thinks, sometimes I just sits. Okay, so I guess the guys in the workshop working with me must think this old man is either crazy or he's damn lazy. But there's a hell of a lot of thought that's gone into it. Unfortunately, that process only started 2 weeks ago, so I can't share it with you. But the relevant technology there is just, don't overcomplicate it. Don't overcomplicate it. Use whatever works fast. Our barrel, so-called barrel, two-stroke barrel, very complex thing, was investment cost using so-called rapid prototyping technology. So what they do is, if any of you have been involved with investment casting, the core is made of wax, and then they cover it with ceramic. You know, they dip it in liquid ceramic. Then they bake it, and in the baking process, well, they dry it, dip it, dry it, dip it, dry it, dip it, dry it, until the ceramic walls are thick enough. And then they bake it to harden the ceramic. And in that process, the wax falls out. So what did the guys do nowadays? They 3D print the core. So you're saving incredible amount of time in manufacturing this core, which is so complex, using the right technology. I also got a quote from China to 3D print this, and for PZ500, we're going to 3D print that baby in 6082 condition T6 aluminium. Lekker. The advantage of that is that Rimpies had to make the barrel in 2 pieces so that the debris, the core, could be extracted after the casting process, the ceramic. Because there are so many passages, it was around the exhaust port, because you've got to cool the exhaust port when it comes out. And they had to make that in 2 pieces, and I don't want to do that because it adds complexity, and my bike is going to push out more or less double the horsepower that Rimpies' bike is going to push out, so I want to keep it simple. And that way I can simplify it. The porting is a lot more complex, so we're going to bypass the rapid prototyping casting, and we're going to just 3D print the barrel clown for paint. The casings were 3D CNC machined out of billet. On the left-hand side there, you can see during the process, that green color is from the coolant that they use. But there you can see the billet that they start off with. And this is what you end up with. A work of beauty. It was such a delight for me to see that thing, because that made the possibility of this engine alive for me. These are pretty complex small parts, and we ran out of machining facility in South Africa in 17.4 pH stainless steel. Any of you have ever worked 17.4 pH stainless steel? That is Gorilla steel. It's serious stuff. It's guys in the armor industry will know that Almox 500 has got a yield strength of 1250, while 17.4 pH challenges armor steel for its yield strength. This is Gorilla steel. We didn't choose the Gorilla steel. It was the only one that the company that we're dealing with could print in metal. So we would have printed it in aluminium, but there you are. 3D printed in stainless steel, near net finished. We just had to drill a couple of holes and put dowels in there and bang, 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 and there you go. So the top right-hand one, that's the shift drum that you saw in the previous picture of Pete of the QC500. That's part of the power valve mechanism, and this is the actual power valve slide that goes up and down and raises and lowers the exhaust port. This is the Excel spreadsheet that I told you about. Koos, forget his surname now, developed that at Ermitech for me way back in, I believe, 1988. I still use it today. I've designed about 40 different prototype armored vehicles. I've used this every time, and I've been damn close every time. Doesn't calculate acceleration, doesn't matter. You get a feeling when you go for horsepower per ton, and if it's really critical to the client, then you go to fancy packages, but user beware. There's the problem with the other simulation packages in acceleration is that they use a so-called lug-down power curve. In other words, they take the engine up to full power, and then they bring it down in steps, and then they will log, at each step they will log the horsepower. But when you're doing a standing start with a turbocharged engine, man, you start with the engine idling at 800 RPM, you put your foot on the throttle, and all the changes is expression in your eyes. Ain't nothing happening, especially with these small capacity high performance engines. Ain't nothing happening, especially now with Euro 3, Euro 4, Euro 5. They're not allowed to make smoke, and the only way to get that turbo to spin up fast is to throw extra diesel in the engine so that you get partial combustion going through the exhaust. Heat spins the turbo up, and bang, there you go. It makes a puff of smoke. You still see modern cars doing that. But in any case, I digress. So the VB Drive and other programs like that don't take that into consideration. It doesn't help. Okay, here's a cool thing. One of the critical things that we had to find out is what is the hardness of the crank material? What material is the crank made of? We have no idea. Pete had heard of these dudes before, and he found them on eBay in the UK. These are hardness testing files. The files, each one of them with a different hardness and with a number scribed in them. So you can see HRC 50, HRC 55, HRC 60, HRC 65. That's Rockwell C. It's a commonly used hardness testing method. To do that, normally you have to go to a test lab, and they've got a machine, and they wear glasses and white suits and all of them, and you've got to rub it down, and you'll see the little indentation. And my experience with that is, man, it's unreliable. Really, I've tested armor plate with that. I got these guys in, and they say, oh yeah, and then the thing cracks the next day. So what the hell? These files, how they work is, you take the file, you go to the piece of metal, and you go, and if it goes, the file is too hard. You take the next one, that's too hard. You take the next one, and it makes a mark. The hardness is between those two things. It's that simple. It cost me $1,500 to fly it in from UK. Brilliant, relevant technology. Got an answer like that. And I've got it in my toolbox. So the next time somebody gives me one of those questions, I'm going to just go, wait, let me get my stuff. Here we're machining the crankshaft. The crankshaft is made from, eventually it was made from aerospace material because we ran out of time trying to decide this, that. And the biggest thing was that we've got to get a serious hardness, 55 Rockwell C, out of the surface, otherwise the oil seal on the two sides of the crank will just wear a ridge in it, and then we're screwed. And in South Africa, you cannot really rely on the guys that do carbonizing and that kind of stuff to give you a straight crankshaft half back after it's been carbonized, because it's a very thin layer. So we used aerospace material 300M. It's even stronger than Almox 500. And it's got a yield strength of something like 1,500 megapascals. I made prop shafts, side shafts out of this for my competition 4x4. This is the real gorilla steel, okay? The other one is the little baby. Any case, 55 Rockwell C. If you've ever worked with hard metals, that's about the hardness of a knife, of a good quality knife. In the old days, we had to machine it via grinding. Grinding is a tedious process, and you can see there's a taper on there. So you can grind this journal, and you can grind that journal, but there are two tapers that have to be ground. Now you've got to turn the machine like this, and so we rough machined the billet out. Came in round pieces like this. We rough machined it out, and I took it for normalizing to get the stresses out of it. We got to about 2 millimeters from the real size. Then after normalizing, they machined it to 0.2 millimeters from the final size. Then I took it back. It had to be hardened and tempered. Then I got it back. It was 55 Rockwell C. This is hard. This is decent stuff. And the company that does the machining for us, PNC Technology, said, there's a rep that came past a year or so ago that introduced him to tungsten carbide tips, new tip with just slight changes to the composition, to the surface coating, wada, 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 wada. You machine that thing with a tip one time, just like that, 55 Rockwell C. Relevant technology. It's new stuff, it's out there. What's the national advert of the old days? Saves you time, saves you money, puts you first. Okay? So that's what you do. Find the relevant technology. Don't go spend 3 weeks finding somebody that can grind this bastard thing. Find something better. The hole where the crank pin moves in, I do appreciate that most of you won't know how a two-stroke crank goes together, but in any case, that's where the conrod attaches to that hole. That hole there. There's a pin, a very hard, very highly accurate machine pin that goes through there. You press fit it in there. And this thing, of everything that we did, that thing gave me sleepless nights. So the relevant technology that we used to get the tolerance of that hole 100%, within 3 microns, is within everyday use. It's used a lot of times. It's called wire erosion. These things have evolved, and the guys that use it, once again, PNC Technologies, they got that hole to within 3 microns of the nominal size. Lacquer stuff. That didn't have to be ground. The manufacturer of the exhaust, this is lacquer because this uses a number of technologies. So it started off with, out of Nielsen's program comes the layout of the exhaust pipe. Then we devised the plan. We cut discs. We cut it in 50 millimeter intersections. Used the 5 millimeter threaded rod. Put nuts on these things in 50 millimeter intervals, all the way to the back. Sometimes they're closer because it's over a bend. You know, like if the 50 millimeters falls just behind that, then Rimpies would put one in there and one just behind it, just to get it lacquered. So that's Rimpies, by the way. He's this much taller than me. He's called Rimpies because he's just sinew, but he's tough as a Rimpie. And so what he then did was, and this is where the relevant technology comes in again. This is Rimpies' motorbike with a plastic printed engine in it. There you can see the balancer shaft, the counterbalance weight on the one side of the engine casing sticking out, all printed in 3D. He put it in the bike, he took this thing, he jammed it into the exhaust port, and he started forming it with his hands all around the motorcycle until he was happy that it was good. Then we had that snake, that boa constrictor, we had it scanned. And this is where the scanning worked, because there's no other way we could have done this. You can't put that on a CNC mill with a digital readout and think that you're going to, this is full 3D. Okay, so, but it's not as complex. And from that shape, we had a CAD designer, and he pitched like hell. Because he had to go from that to that. And from that, he then did development of all these pieces of steel, which we had laser cut. There's your exhaust. Bang, bang, bang. Paint by numbers. Each one of them numbered. There's a front and a rear arrow on it with an index mark. So you hand bend the pieces. Yes. And then you weld them together so they become pieces, and then you align them up the marks. Lekker, eh? So this is where technology meets an artisan. The guy that does the bending on those things, that does the welding there. Man, look at it, it's exquisite. You've got to see it on the bike. There it is, fitted to the bike. It's a piece of, it's a work of art. And the sad thing is, Rimpies is going to bend it broken on the rocks in the soup. And we're all going to cry for a little while, but they make a very nice beer in Lesotho called Maluti. I think a couple of cases later of Maluti and we'll be okay again. And then we'll panel beat it. Okay, I'm going to end off now, and I don't know how much time I've got. Wow, I've still got 10 minutes. Am I lying? Am I way over? I don't know, I have no idea. Okay, alright, so I'm having fun. If you guys are having fun, if you want to get up and scoot, you're welcome. I'm going to finish now. So, this is where TANDM comes into it, with relevant technology. They do all these, you saw the cameras they can do, you know about the data acquisition systems they have, etc., etc. So, what we have is, this is not 100% TANDM, but the friction coefficient on the salt is bad. It's between 0.45 and 0.5. So wheel slip is a real issue. So what we're doing is we're doing a Boermakkerplan ABS sensor type system. So we've got pole wheels on the front and the rear, which we laser cut. Then we put sensors on there. Then we have a little comparator that then tells us when the rear wheel is slipping relative to the front wheel, and there'll be Christmas lights on the dash, green, orange, red. If it says red, then I got to tap off a little bit, because the real danger is that you can shred the tire because the salt is very abrasive. Any one of you who's ever played with a two-stroke will know that if a two-stroke seizes, firstly, you're going to land on your head, because it locks up the back wheel, and man, there's ADOM. And the second thing is it costs money to fix. So you don't want that thing to seize, especially not this thing, especially not at the speeds that we plan to hit. By the way, the current world record without a fairing is 230 kilometers an hour. With a fairing, it's 253 kilometers an hour. We're aiming to hit between 260 and 280 km an hour. I'll be the rider. I'm really looking forward to it. So what we've got here, I've circled it in red on the Dash 2 display, which is from Race Technologies, yes. It's displaying there, the big one, that is exhaust gas temperature. That's where you're going to rise and fall, because that'll tell you things are bad inside there or things are good inside there. We're displaying both water and oil temperature at a little bit smaller because it doesn't happen so fast and it's not so catastrophic. We're displaying gear position. It may seem whimsical, but when you're traveling at 260 km an hour with a wide open two-stroke pipe behind you and a 44mm carb sitting under your face here, the noise is deafening. You can't hear diddly squat. And if you're in the wrong gear, you're wasting speed. You've got to be in the right gear. And you've got to be in the right gear at the right time. So the dash 2, they call them Christmas tree in the old drag racing days. They also call them idiot lights. So as you get close to the gear shift point, the idiot lights will start flashing, and when it gets to red, you must change gears. That's the optimal point. And the optimal point, interestingly, is not the same RPM for each gear. Because the gear spacing is not the same. And that we get from the Excel spreadsheet which has the cascade curves. So from that we can pre-program in here for each gear. So it knows which gear it's in and it knows what's the optimal shift point, and it helps me to accelerate faster. This is not all about acceleration, but you've got to get there, and the sooner you get there the better. And pray for a tailwind while you're going. We show on the display, we show GPS-based speed, pretty accurate. It's got a 20 Hertz little antenna that feeds into the data logger, which I'll show you just now. And actually the Dash 2 has the capability of doing that all by itself, just with the remote antenna. It'll give you the speed, very lacquer. There it gives you the RPM. Also important, feedback to the rider. I've got to know. I don't know if I'm going to be able to see it like this on the salt pan, but there we go. So this is the DL1 Club data acquisition unit that we use. It comes automatic. It comes supplied with 3-axis accelerometers, so you can use that. You've got to be careful how you use it. If anybody that's ever used accelerometers will know about that. And it's with the 20 Hertz interface to the antenna. It gives you very, very good speed data. It also gives you positional data. And with the associated software that is supplied by Race Technologies, there you can see somebody that's gone around the racetrack, and it gives you sector times. And in our case, that's not important. But what we're also putting in there, what we're logging at the same time, is all the parameters that are shown on the dash in front of me, plus additional stuff. And so you do the run to the end of the thing, then you slow down, then they pick you up with a truck. Well, my team picks me up with a truck, and it's a bakkie, eh? In America, it's a truck, it's a bakkie. So I've also started talking about my truck. I've got a Land Cruiser truck. Any case, while we're busy loading all this stuff, because this is going to be low slung, while we're loading this stuff onto the truck, Jock, who's our test engineer, will take out the SD card out of this, bang it into his computer. He'll know what I want to see. While we're driving back, we're going to talk about the stuff, because our turnaround time has got to be as fast as possible, so that we can get in as many runs as we possibly can in a day. So we want to get to the back of the queue on the other side, ready for the next run, knowing what we want to do. Are we going to do a gear change? We're going to do a jetting change. Am I going to take a poo so that I lose a kilogram or something? Whatever. We've got to know it by the time we get to the start line. So this software that comes with the DL1, really amazing for testing. You can do all kinds of tests with it. The genetic guys will know it. So there you have probably the only completely manufactured South African motorcycle engine in the history of the country. Probably. There may be exceptions, but show me the proof. We designed and built this from a clean sheet of paper, 7 months and 20 days, and we started it. And This is the starting video, and I'm going to play you this video. This is the complete video from when Rimpis asked me, should I try and start it? I said yes, and I switched on my cell phone. The complete video is 1 minute 40 seconds long. Watch this. Look, madam. Let's go. Okay, where's the sound? Okay, there it is. Okay, so he tries to kick it. And then as a 5 minute two-stroke this kicks back, and he doesn't have his boots on, he's going, ina. So it's got an electric start. He's thinking about trying it again, he's going like, no. So we've got a decompression valve in there. That's it. Yeah, that's me. I could not believe it. Okay, and that's like, yeah, baby, yeah. Lekker stuff. And there's the goosebumps. Okay, it's an amazing thing that we achieved. We believe so. We're not aiming to do anything specific at the roof other than arrive and do our bloody best. We're not going to win anything except the undying love and adoration of our wives and friends and family and people that really know what's cooking. For me, we already won. We achieved an amazing goal. I bid you all farewell. Please, let there be questions. Any questions? Come on, guys. Yes.
You still, Elton?
So the spark that started it all was
Stupidity. So you can follow us on YouTube. It's very simple. Team Matjien, spelled with a T. Team Matjien. So it's at Team Matjien on YouTube. There's about 5 videos. The first video's title is Why. Why did we do this? It's about 24 minutes long. I think it's entertaining. The second one is designing it, and the third one is building it. And then there's another interview that a designer, journalist did with me and Rimpis, and it's all very entertaining. The reason why, in the 80s, big bore two-strokes weren't it. Only the strongest of the strong could ride them, could even remotely master them. And Rimpis was in high school. They had no money, couldn't buy one. And then they went completely out of fashion because we almost know we're socially responsible. We've got to look after each other, and we don't want to hurt people or what. You can't buy one for the last 10, 15 years. That's when Rimpis had money. So, and last year he came to me, because we have this racing team, we started racing the Roof of Africa together in 2004. I'm the team manager, I'm not a Roof of Africa racer. I'm a racer. I'm a full out racer. And Rimpis came to me, he said, let's do this. And I said, yeah, and I let him go. And then in December he came back and he said, come on, let's do this for Team Matjien. And I said, yeah, it's like Then in January, he showed me a picture of a company in Canada that sells a kit like that. Kit sells for, I think, 120,000 Rand over there. Then you got to fly it here, and then you got to take out the big skiller and give it to the customs guys, and then to SARS. And by the time you've done all of that, I don't know how much it costs. And I said to Rimpis, the hell with that, let's do our own. It's going to cost us probably more than that, but let's do our own thing. And to put all your minds at rest, there is no commercial plan with this endeavor at all. The commercial endeavor is, it's like a roller coaster ride. We're in this to have fun. It's a journey. It's completely for fun. 100%. If you want to buy one, BRC in Canada will sell it to you. Right, thanks. Thanks, Quest. That was awesome. Thank you very
Any
much.
more questions? Thanks, guys.